Hey, what's up, guys? So in this video that we're gonna talk about is so-called Gaussian tail bounds, and I recently encountered it, but I found that I have not yet like fully derived this in my career, right? So now I will spend some time to give the quick derivation. Okay, so we will do doing like simple single variable case, but once you understand it, then you can check out some paper that there are some paper talking about a multivariate case. Okay, so we know that, right? So let me just do some sorry. So we know that there's many so-called concentration inequality in the probability theory, right? So basically, they want to ask the what's the following, right? So given x, there's the probability distribution. So one idea is that you want, let's say, its potential value is mu, and let's say you know the variance, right? So you know the variance is sigma squared. Okay, so one like ask the following, right? So this is that people want to ask, and for general that distribution that you can only notice by like one of the k-square. This is called the Chebyshev inequality. Maybe you can do something better, but almost this. Okay, so but the natural thing one like to ask is the Gaussian, right? So people like to ask Gaussian. So there's a sort of question that we want to ask is the following, right? So we want to say that your x is some mu sigma squared. So let me just quickly remind you, this is the normal distribution. So the probability density function is 1 over square root of 2 pi sigma. X minus this, is this, and dx. Okay. So this is the probability distribution. Okay, basically Gaussian interval, right? You can check the integration is one. Okay. So we want to ask what's if x is distribution from normal distribution, comes from normal distribution, we want to ask what's bound, that so-called tail bound. So tail bounds tell you that what's the probability that x minus mu. What's the we want to ask what's the probability of this constant. Okay, so we can ask p. Okay, so we want to ask what's this. Okay, but this looks okay. So there are like many ways to do this, right? So one simple way, right? So let's say you want to do a simple way. So one simple way to do this is that you just right, using your mathematics and try to do this kind of estimation. Right? So basically, you just do this t minus right. So mu plus t infinity and do this. Okay, so I will assume that t greater than 0. Okay. So obvious that you can try to do this, but I mean it's hard to do it, right? So maybe you know some inequality, but this is usually not the way that people in the probability theory they will not doing this integral. Okay, so another way that we can get this tail bound is using the idea called Chernov bound. Okay, so let me just quickly quickly remind the Markov inequality. So I think I will not prove this because I will already prove it like 100 times. So idea is that if you have a probability x greater than 0, and the probability of the probability x greater equal to a, obviously a need to greater than 0. That's equal to expectation value of x divided by a. Okay, so this is very simple that you can prove by using the area. Okay, so it's almost trivial. Okay, so in general that you don't know x, right? So in general your x is not positive, right? So the way to do this is to do the exponential, right? So idea is that you define a variable y, which is called exponential x, then y will be greater than 0. Okay. And but you can put lambda, right? For some particular lambda. Okay, then lambda greater than 0, then you can optimize lambda to get a bound. Okay. So let me just write down. Right? So we have this probability of x minus mu greater or equal to t. Let's say we do some exponential, right? So we can, it's the same as probability of exponential lambda x minus mu greater or equal to lambda t. So let's say lambda greater or equal to 0. And this is less or equal to, use Markov. You get the exponential of expectation value of this x minus mu. Okay, so this is basically the somehow like the moment generating function. So divided by the lambda. Okay, so you just find the lambda, right? So just infiniment of lambda greater than 0. Okay, so the final simple thing is just to compute the normal distribute, also compute the moment generating function of Gaussian. Okay, and this is like simple calculation, so I will not do here, but let me just write down answer. Okay. Okay, so this is proof by yourself. Okay, so this is simple exercise that you can do this. Basically, just some integration, right? You just write out definition and do a change of variable. It's almost trivial. Okay. Okay, so once you have this, then you immediately have something, right? You immediately have this. So let me just write down, right? So you have so equal to divided by the lambda t, right? So you get okay. So you will need to find the lambda, this lambda such that this guy is small, right? But this is quadratic. Okay, so very simple. That right, you want to optimize lambda, right? So obviously that let's see. So you have this, right? So we want to find the lambda. Right? So okay, so it's like if you have a squared plus bx plus c, you know that the maximum is at sorry, the minimum or minimum maximum is minus b divided by 2a. Right, so in this case, that is t divided by lambda, right? 2a is sigma squared divided by 2, so it's t divided by sigma squared. Is this correct? Check it, check it. Okay, so now you can do this, right? So you do this, you get this t squared divided by sigma 4 sigma squared divided by 2 minus. Okay, this, right? So you get minus exponential minus t squared divided by 2 sigma squared. Okay, so finally, so this is our results. Okay, so so the x minus mu squared the t is basically this. Okay, so but this is hard to remember, right? So right, how to remember? So usually you will see the following results. So this is called tail bound. So you can like choose the x to be the normal distribution, standard normal distribution, but with normalized like standard variables to be 1, and shift the mean to be 0. And usually you will heard about these results, right? So this is exponential small. And this is famous tail bound. So just this. Okay. So minus a squared divided by 2. So in this case, that in this kind of like spirits, then one can define an idea called sub-Gaussian. Okay, so basically sub-Gaussian is like you just take a list and say that, oh, if your probability distribution for some a, for general a, there will be some constant that on exponential such that your tail, right? Your tail is exponential small. This is why it's called tail bound. Okay, and so one can generalize this to the multi-variable, right? So, but there's a lot of paper that compute this, right? So basically, you want to ask what's the general case? Let's say x. Let's say your x is some. Let's say you solve for 0 for some particular covariant matrices. And you can ask a similar question, right? What's the component y that x1 is something x equal to something. Okay, so this is quick explanation of the derivation of tail bounds, and hope you guys subscribe to my channel.